am. This time we have Zac, which is going to be talking about bugs. All applications have bugs, and this presentation is interesting because he's going to be providing about tricks on how to find them. Zac, thank you very much for being here this afternoon with us, and it's all yours.
Thanks very much. Let me share my screen. So, welcome to my talk, Fantastic Bugs and How I Find Them. It's about the way that I test code, and I'll be live coding to rediscover some of my favorite bugs as part of that. If the tools I'm using seem futuristic, it's not just because it's Saturday morning here in Australia, but because I've been working on this as both part of my open source work and also as some research projects that I've been working on for the last few years. But before I get into it, I want to start with an Australian tradition called an acknowledgement of country. This image is of my hometown of Canberra, but Australia, like most of the Americas, is colonized land. And I want to acknowledge that before I started living or working here, or before my family arrived here in Canberra, this was the traditional lands of the Ngambri and the Ngunnawal peoples, who have occupied and built technologies and learned and taught in this land since time immemorial. And I want to pay my respect to any First Nations people who are here with us today. So, this is a talk about bugs. And I promise I'm not going to be talking about the really nasty kind of bugs, which is a bit of a risk if you do a Google image search for loads and loads of bugs. You might get things that you don't want to look at or show to everyone. But I'm not just talking about bugs, though that is a big part of it. I'm also talking about how I find bugs, which is by testing. And for the purposes of this talk, I'm going to define testing as that thing where we execute code in order to find bugs, or sometimes in order to find regressions, which are not just any bug. And that means that we have to choose inputs to our code, we actually run the thing, then we check that it did the right thing, or at least check that it didn't do a particular kind of wrong thing, like raise an exception, and then we repeat that as needed. This definition excludes a lot of really useful techniques for writing correct code. Those include things like type checkers, such as MyPy, linters, such as PyLint or Flake8, code review from your colleagues, or just plain getting enough sleep. It turns out when you do software engineering research, the biggest thing you can do to write less buggy code is to have a team which is less stressed, who trust each other, and who do in fact get enough sleep. But I'm just going to pretend that sleep and coffee don't exist and talk about software testing. And in order to demonstrate these, with apologies to my friend David, who is very sick of people who demonstrate by reversing lists twice, in order to avoid driving David to drink, I'm instead going to talk about sorting lists, which is totally different to reversing. So let's imagine for a moment that we, for some reason, didn't trust the sorted built-in in Python. And we wanted to test that the sorted built-in does in fact sort lists correctly for us. We might write some tests that look something like this using Pytest. We assert that if we test the list, or if we try sorting the list 1, 2, 3, that's integers, then we get the list 1, 2, 3 back. And if we try sorting 3, 2, 1, where the numbers are floats, we get 1, 2, 3 as floats. So it works for floats as well as integers. And we can also test that if we sort B, C, A, then we get A, B, C. So sorting should work even for non-numeric types. If we start thinking that we might have to maintain this test suite though, we might want to actually try a parameterized test, which looks something like this. A parameterized test lets us save time by just listing out the inputs paired with, in this case, the correct outputs of the given function. And okay, when we're just talking about 3 examples, this hasn't really brought us much. In fact, we've lost a little bit of expressiveness about the specific types that we expect in each case. But what we've gained is making it much easier to add additional cases as we find them, maybe from user bug reports or production incidents or just thinking harder. The catch is that I don't really think this is automated testing, because in some sense, what we've done is we've just recorded the results of skilled human labor. We've had to think up by hand, what should every input and what should every corresponding output be? And this image is of a thing called the Mechanical Turk, the original that Amazon service is named after. It was a mid-1800s automaton, which purported to be a clockwork chess-playing robot. At the time, playing chess was considered to be something that was infinitely beyond the capability of machines. Of course, now we know that it is in fact possible for a machine to play chess, but to play chess at a grandmaster level is certainly beyond the capability of 18th century clockwork. The lesson here, I guess, is that when you see something that looks really impressive as machinery, there's a good chance that it's just hiding human labor somewhere inside it. So let's think a little more about how we might be able to automate, truly automate some more of this process. One great starting point would be if we only had to come up with the inputs. So if we didn't need to calculate the corresponding output by hand, this would allow us to test things where we didn't know the correct output immediately, or where it was too much trouble. And the easiest way to do that would be if we had a trusted implementation of sorting. Maybe we don't trust Tim sort because it's a complicated algorithm, but we implement bubble sort by hand, and we're sure that even though this is too slow for use in production, it's trusted enough that we can compare it to our fast implementation for testing purposes. This is actually a pretty realistic scenario. Often, for example, you might have something like this where you could write your own really slow version, which is simple enough that it's obviously correct. Or you might have a multi-threaded version that you can run with a single thread to check that you don't have threading issues. But even if you don't have a trusted implementation, you can often still find plausible bugs in the output of some function. For sorting, for example, we should be able to check that no matter what our result is, the elements of our result sequence should be in non-decreasing order. That is, for any A and B in the pairwise sequence, the first element should be less than or equal to the subsequent element. The only problem here is that if we're working with a person I like to think of as the enterprise developer from hell, we might have a great performance optimization that would pass this test. We just always return the empty list, which we can do in constant time, and the test passes, so it must be a valid sorting function, right? Well, of course, that's not valid. So we might say that as well as our result being in sorted order, we need to have the same set of elements and the same number of elements as our input list. And I think this is actually a remarkably good test for sorting. It's pretty hard to imagine a variant which would pass code review but still fail this test. But if you were sneaky in code review, you might still be able to do it. For example, if you replaced the list 1, 2, 1 with 1, 2, 2, this test would pass. You'd have the same number of elements and the same set of unique elements as before. So if we look up the mathematical definition of sorting, we require that the output is in sorted order and that the output is a permutation of the input. That is, it's just rearranging the same elements. And so, all right, we can just check with inner tools that it's a permutation of the output. The only problem is that this is horribly, horribly slow, far too slow even for our test suite. And so to be sure, we'd want to use collections.counter to say that we have the same number of each distinct element as we did in the input. So congratulations, we've just discovered property-based testing. Our two properties for sorting, which fully specify the function. Every correct sorting function is uniquely defined by these two properties, that the output is in order, and that we have the same elements in the input as in the output. I do want to note, though, that you don't need a full specification to find a lot of bugs. I actually really like this test with the length and the set because it's easy to think of, it's clear what it's doing, and you don't need fancy libraries that people might not understand. Partial specifications are still really useful for finding bugs. The catch here is that no matter how rigorously you analyze things, or how creative your imagination is, there are some test cases that are just never going to occur to you. And so the bit we haven't automated is still here, where we have to come up with the inputs by hand. Is there some way to do that as well? Well, with apologies to Thomas Schelling, whose quote I butchered, there is. My library hypothesis is in fact centered around a way of generating inputs which wouldn't have occurred to you. So if we use the same test body with hypothesis, we can say that given an argument which is either a list of a mixture of integers and floats of any length, or a list of Unicode strings, again of any length, then the same test should pass. Do you think it does? Well, it turns out that this test will actually fail, because hypothesis will generate not a number. And not a number is a special floating point value which compares unequal, no matter what the comparison is, to anything else. So when we go back through and we do this comparison that A is less than or equal to B, if one of those is not a number, this assertion will fail. And so it turns out that to correctly specify the behavior of the sorted built-in the presence of not a number takes a more complex set of properties than we have here, because we've been implicitly assuming that every possible element can be compared either less than or greater than or equal, but not more than one of those, to any other element. And in general, that's just not the case. So by writing this test for sorting, a built-in function which I think we all understand quite well, we've actually discovered something new about Python's behavior. And so the moral of the story, to the extent that there is one, is that I think you should use property-based testing. And in order to do that, there's basically a three-step plan that I'm going to walk you through before we get into how I discovered some of my favorite bugs. That foolproof plan is to pip install hypothesis, or if you prefer Conda, you can Conda install hypothesis. You can skim the hypothesis docs, and then pretty soon after, you'll be finding a lot of bugs. But as to how soon you find bugs, well, we can make that a little faster using a tool called the hypothesis ghostwriter. And this was a response when, back in the before times when you could physically go to conferences, I would talk to a lot of people and they would say, oh yeah, hypothesis seems cool. I'm just not sure how to apply it to my code, which is fair enough. I've showed you some very specific properties for the sorted built-in, but there's also a more general set of properties that can be applied to almost any code. And that's what the ghostwriter is designed to help you do. Once you pip install hypothesis, you get this command line terminal thing. You've got hypothesis write. And if you ask hypothesis write for help, it tells you that it writes your tests for you, which is a pretty neat kind of capability. And we've got a couple of options here for standard types of properties that we might use, as well as whether we want Pytest or unit test star. Let's start by getting it to reproduce the kind of test that we wrote earlier for sorted. Of course, that's the sort ed built in, which hypothesis recommends we use. So what have we got here? The ghostwriter will tell us how to import hypothesis, that we want the given and the strategies, given function and the strategies module. And then the ghostwriter will point out that we've actually got three arguments. We've got the iterable that we want to sort, an optional key function which defaults to none, and also a Boolean flag for whether or not to reverse the result. So this is in fact, in one way, a more general kind of test than we'd written before. It's not dealing with floats, but it's considering the key and the reverse argument. On the other hand, this function doesn't have any assertions in the body. It's just calling the function and seeing if it crashes. It turns out, at least on my code, that's embarrassingly effective as a starting point. But we can tell the ghostwriter that the sorted function is what we call idempotent, which means that if we run sorted on its own output, we don't expect that to change. And if we pass -- idempotent to the ghostwriter, it will write a test that checks just that our preliminary result comes from sorting our iterable, that our repeat is from sorting our result, and then assert that those are equal. And I would write an additional test that checks those properties we discussed earlier, but I think this is a pretty good starting point. A different property that we might want to check is the equivalence of two functions. So this is the trusted sort function pattern that I talked you through earlier. In this case, we might say that the ast.literalEval function should be equivalent to the eval built-in, since they both evaluate Python code. And so the ghostwriter will say, well, if you take an empty global namespace and a local namespace and a node or string in a source code, so it hasn't quite noticed that those are the same argument semantically to two different functions, and we calculate the result for each function, then they should be equal. So you'd have to edit this function by hand to collapse these two arguments together, and also maybe to ensure that it only generates strings which are valid Python literals. I have a package for that, which we'll see later in the talk. If you have something like a binary operator, there are a number of classic algebraic properties of binary operators, and this is actually where the term property-based testing originated in Haskell back in the 1990s. It doesn't come up quite so often in Python, I'll admit, but where it does, the ghostwriter can recognize that, and it can check that your operator is associative and commutative and has an identity element. That is, a plus b equals b plus a plus 0 always equals a for any a, and that no matter how you group the brackets when you're adding three different numbers, you should get the same result. All right, on to some round trip examples. And round trips are probably the most powerful single property you'll see. They're applicable to almost any code because no matter what your code base is, you're likely to save data to disk or to a database or send it over the network and then bring it back. And in this case, the ghostwriter can notice that there's a decompress function in the same module as the compress function. And it's smart enough to guess that that means that if you compress something and then you decompress it, you should get that same thing back, no matter what your input is. So for this test, you just need to replace data, the nothing strategy, with the binary strategy to generate byte strings to compress, and you'd be off. A more complex example might be JSON. I'm sure we're all familiar with JSON, but you might not have seen the sheer variety of arguments that the Python JSON encoding functions have. You've got whether or not to allow NAND, check for circular things, an encoding class, default value, ensuring ASCII output, the indentation object. It's kind of a mess, to be honest. So I cleaned that up a little and said, look, we don't care about all of those arguments, only some of them. But more to the point, I've defined our JSON object using the recursive strategy. And this says that the definition of JSON is that it's either none or true or false, or a number or a Unicode string, or a list of any JSON object, or a dictionary mapping strings to other JSON objects. And then we have a simple round trip that we dump our JSON object to a string, load it back in from a string, and then assert that we have the same object again. Do you reckon this is going to pass? Let's run it with Pytest and find out. It turns out that not only does this test fail, but Hypothesis finds 2 bugs with a single test. Both of them, to be honest, in our understanding of what JSON encoding was meant to be doing. So the first is that if our object is not a number, then of course not a number is unequal to itself, so the test fails. All right, that one's kind of obvious. The other one is that if we pass allow NAND equals false and our object is infinity, the test also fails. And for this, it turns out that the JSON standard doesn't actually permit non-finite numbers, which is infinity or not a number. And the Python standard library put that option to strictly enforce the specification, which most JSON implementations don't do by default, with an allow NAND argument, rather than something like enforce finite equals true. Weird argument, but hard to change due to backwards compatibility. So if we compare our fixed test, then what we might do is say, well, we'll always allow non-finite numbers. just for the sake of simplicity here. But we'll assume that the object is equal to itself. And assume is another function out of hypothesis. It's basically the same as an assert, except when it fails, instead of saying this test fails, it indicates to hypothesis that the input is bad for some reason. In this case, that we don't expect the test to pass unless this is true. So if you find something that violates it, just try another example without treating that as failure. All right, I'm going to leave what happens next as a bit of a spoiler for later in the talk. So, time to talk again about some of my favorite bugs that I've encountered over the years that I've been using a hypothesis. And for this portion of the talk, I am going to be live coding to try to walk you through the process of how I discovered those. So let me pull up a Jupyter notebook. So the first thing that I kind of want to discover is, what do you think is a nice property of the length or the range built-ins? This has got to be true, right? That if you construct a range of some positive number, then that should always be true. So we could go given integers, min value is going to be 0, then this should pass, right? Will it? It turns out that we actually have an overflow error, which is kind of strange, but makes sense when you think about it. And since I found this is now actually documented on the length function, Python assumes that a sequence can only be, at most, the length of the maximum pointer size for your platform. That is, you can't have more than a 4 GB collection on a 32-bit platform, or more than a 2 to the power of 63 size collection on a 64-bit platform. And that's a perfectly reasonable assumption if the collection is actually materialized in memory. It turns out, though, that range, because it's that special object that doesn't have to hold all of its intermediate values, in Python 3, you can construct a range with so many elements that you can't point to them all with a 64-bit pointer. That happens efficiently in Python, but it doesn't quite work according to the length built in. It just causes an overflow. And this is just considered an implementation issue rather than, strictly speaking, a bug, because it's a huge performance improvement, and let's be honest, there's not really much use for ranges this big. So if we just say that our maximum value is 2 to the power of 63 minus 1, then our test passes, as we expect. So let's have another look at, well, let's be clear, the thing that I was going to talk about here with the JSON encoding. So let's have a look at that. If we say that our list contains a list of float man, right? Is the list equal to itself? Yeah, for some reason that list is considered equal to itself. But if we round trip it through JSON, it's no longer equal to itself. What? What about if we copy the list? Okay, so the list is equal to a copy of itself, but it's not equal to JSON encoding itself. What about deep copy? Okay, but it's still equal to a deep copy of itself. Does anyone want to guess what's going on here? Let's run through the last part of this JSON example and see if you can work it out. So our first naive attempt to fix that test has failed on exactly the list containing NaN example that I just showed you. So our real fix would probably just be to exclude NaN, at which point the test passes. The test passes. The test passes, right? Okay, yeah, the test does pass. Phew. Okay. So what have we got here? We can see that NaN is not equal to itself, that a list containing NaN is equal to itself, that JSON round tripping it is unequal, that copying it and copying it is equal. What is going on? Okay, I'll admit, spoilers, I just went and looked at the CPython source code to solve this. And it turns out that there are some performance optimizations in the implementation of list equality. The first thing that a list will do when you compare it to something else is check if the other thing is the same object. So ls equals ls will always be true, no matter what its contents are. However, the second thing it will do is check the identity of each element of the list before doing a deep comparison by equality. And that's a performance optimization because it lets you skip deeply nested comparisons, which can save a lot of time when you have nested collections. And so because the element is the same by identity, we only have this single floating point NaN object by ID, then this will also be true. And it turns out that deep copy doesn't actually create a new object when you do this. So if we go for the ID of the first element of ls, then we get, our ID. It's a pointer practically to that NaN that we created earlier. But if we do a deep copy, we get the same thing. And so that's basically where we come from. But if we ask for the ID of the JSON round-tripped version, then we get a different floating point NaN object. And that's the point at which we actually compare them by equality, and then it fails. So there you have it. I actually discovered this originally when I was writing up a quick demonstration slide for a conference talk about property-based testing. And I wrote up my JSON round-tripping example and was completely baffled for an entire afternoon about what on earth was going on. But it turns out that there is this very reasonable performance optimization, which makes CPython a lot faster at the cost of occasionally confusing people when they have NaN in their data structures. All right, time for another example. Let's check something with the decimal type. So the decimal type is a kind of real number object which has user-supplied precision. So if you're doing calculations with money, for example, sometimes people use floating point numbers, and that's usually a bad idea. Sometimes they represent the number of cents as an integer, or some fraction of their currency as an integer for a kind of fixed point representation, so it rounds correctly. And if you're doing that in Python, you might as well use the decimal type. Decimal is a particular specification which originally comes to us from IBM via COBOL, but the short version is it's a number type, kind of like float, kind of like int. And so we can also check, for example, that decimal is a hashable type, which is great because it means we can put them in sets or use them as elements of a dictionary. So let's just check that, right? If we go decimal to null, then sure enough, we have a dictionary where we've hashed the decimal 0 value and it goes to null, right? And sure enough, we get null. No problem. So decimal is hashable. So far, so good, right? Shall we check whether it's always hashable? Oh boy, it turns out that there's a special kind of non-number called a signaling NAN. And where normal NAN, or quiet NAN as IEEE 754 nerds would call it, normal NANs just kind of silently propagate. Any operation or numeric operation on a not a number itself becomes a not a number. But any operation on a signaling NAN instead becomes an error. And so what we've just discovered is that there's a particular instance of a hashable type which can't be hashed. That becomes kind of a pain when, for example, you want a set of decimals using a hypothesis. You'll get this internal error where hypothesis goes to generate that and then it fails. So what you might want to do instead is use the from type function. Say that, well, if you go for a set of decimals, then you really did mean that, and hypothesis will internally filter out the signaling NANs for you. That was an adventure and a half to discover and debug. In fact, I've also found a related issue in NumPy one time, where normal floating point numbers can technically be signaling NANs as well, though most code doesn't notice. And that's because the bit pattern for the mantissa of a floating point number is particularly specified. If you have an all zero mantissa, then that's a standard NAN. If you have a non-all zero mantissa, then this is a signaling NAN. It's a trick that people often use to pack up to 52 bits of other information into their NANs. Kind of a tagged union approach for floating point numbers, which is great until a particular bit of Fortran or C code inside of NumPy sets but forgets to clear a particular CPU flag, which then causes an internal error if you generate a NAN which has a non-standard bit pattern. In CI, where the representation is just NAN regardless of what you do. That one took us weeks to work out. All right, a few final examples here. Suppose that we have date times. Date times are useful, right? What could possibly go wrong when we don't even have time zones? We'll ask hypothesis to generate date times for us. If I've remembered my methods correctly, this one actually passes. It turns out for the standard library date time, the from ISO format things always pass. But they didn't always, and in particular in the dateutil library, this once found an error where if you picked the 4th of April in the year 1, the parser would get confused as to whether the year 1 was the month or the year. And so this would be inconsistent for any 2-year dates. Enough of those bugs though. The last ones I wanted to mention were a CPython parser bug, which was down to the Hypothesmith tool that I built. Where is this? Hypothesmith is a hypothesis strategy for generating Python source code. Of course, you should not execute code generated by strategies that generate arbitrary code because that gives the fuzzer arbitrary code execution. But it's very useful if you're building a linter, an auto formatter, or a new parser for CPython, where in the lead up to 3.9, this actually found a new segfault in the parser, and later found a couple of null pointer exceptions in there as well after release. So that's the talk. We are now at past, and I am happy to take any questions from the chat. I hope you've learned something, and I hope you find property-based testing useful.
Thank you, Zac. And actually, we ran out of time, and this is why, for any questions that you have, and I imagine that you might have some questions. The chat, they were all during the presentation enjoying and discussing about your presentation. So it was very good. Thank you very much. Go to the lounge where you can get with Zac so he can answer any doubts if you have any. Again, Zac, thank you very much for being here with us, especially
it's an absolute pleasure.
It's a different time, and you made the effort to be here. So we really appreciate it. See you at the lounge.